Now, let's consider the operation of two water distribution systems. In both systems, the utility tanks have 40 meter cubics of water. However, consumer A only needs 30 meter cubic, while consumer B requires 10 meter cubic of water. Based on the consumer's demand, this system will perform a step-down function. Firstly, switch A and B are turned on to allow the water-generated tanks to generate and store water according to the consumer's demand. At this moment, we can see there is a continuous water flow between the utility, water generated, and consumer tanks. Thus, as similar to this condition, when the transistor in the DC converter is turned on, there is a continuous current flow between the DC supply, inductor, and resistor. In this condition, the inductor is energizing to store the magnetic field. Once the water-generated tanks completed their tasks, both switches are turned off. Automatically, the uncontrollable switches are turned on. At this moment, the utility water tanks are disconnected from the consumer's tanks. Hence, the water-generated tanks will act as the water supply to the consumer tanks. Thus, in the operation of the DC converter, the turn-off transistor will disconnect the DC supply from the load, and eventually the inductor will de-energize to supply current to the load. Based on your observation, which switch should be on longer to generate water in the second water tank, where this water reflects the consumer's demand? The answer is A. Due to the demand, the turn-on time of switch A is longer than switch B. Hence, it will affect the duty cycle of the switch since the turn-on time is directly proportional to the duty cycle of the power switch. Based on these two systems, switch A has a higher duty cycle than switch B. Lastly, let us compare the system diagram with the circuit topology of the DC-DC buck converter. According to the equation, if Vs is constant, hence the output voltage is directly proportional to the duty cycle. Therefore, it verifies the conclusion made in this discussion.